Now we discuss analysis of variance, or in short Anova. This topic, analysis of variance, deals with study of variations in a set of observations. This is introduced by Professor R. A. Fisher when he was studying the data related to agriculture. Even though the title is Analysis of Variance, it is dealing with test for equality of means of several populations. In the topic of testing of statistical hypothesis, we have discussed a method to test equality of means of two populations. There the statistic used was t equals x1 bar minus x2 bar root of sigma 1 square by n1 plus sigma 2 square by n2, and it follows n01, and the null hypothesis is h0 mu1 equals mu2. So here mu1 and mu2 are the means of two populations, and the test is regarding equality of means of two populations. And this test is considered in three different cases. One is the population standard deviations, sigma 1 and sigma 2 are known, and second is sigma 1 and sigma 2 unknown but samples large in size, and finally sigma 1 sigma 2 unknown and samples small in size. In all these cases, our plan was to test equality of means of two populations. But there are many situations where we have to consider equality of means of several populations. For that, we can effectively make use of the technique of analysis of variance. For example, when we are studying the yield of latex from some 5 or 6 rubber plots, and we assume that all the factors influencing the yield of latex other than the fertilizers are kept same. And our aim is to test whether all the fertilizers are equally effective in the yield of latex. So we have many factors influencing yield of latex, like the type of the sapling, the rainfall, sunlight, the landscape, and many factors which are listable or cannot be listed. And also the factor under our study is the influence of fertilizer. So our aim is to examine whether all these fertilizers are equally good in this yield of latex. Or another case, suppose there are 5 or 6 batches of students studying same subject of a program. Then we assume that all the students are from same socio-economic background, academic background. All the factors influencing their performance are identical. The only factor influencing our discussion is the performance of the teacher. So we will test whether all the teachers are equally performing or same level influence in the performance of students. So there all we can consider the case of testing equality of means of several populations. So this is a very powerful device in testing of hypothesis, and it is applied by all researchers or all analysis in various disciplines. Now, the causes of variation in a set of observations can be broadly classified into two. One is assignable causes and the second is chance causes. The assignable causes are identifiable to the investigator. He can identify and he can correct it also. But the chance causes are beyond the control of the investigator. For example, the yield of lactose we discussed earlier. These all the causes we discussed are identifiable or can be corrected. Suppose all the factors, including the fertilizer, same for all the rubber plants. Even though we are not getting same yield of lactose from all the rubber plants, there are some variations. So even though the fertilizer level or the landscape or the sunlight or sapling or all the factors listable or cannot be listed, same, we don't get all same reading from all the rubber plants. So there are some other factors which are beyond human control, which are random. Such causes are known as chance causes. So in the above example, this fertilizer is an assignable cause, landscape is an assignable cause, rainfall is an assignable cause. but chance causes are beyond our limits. We cannot control these chance causes. So the variation is due to totality of assignable cause and also chance cause. Here we consider the notation x11, x12, etc., x1, n1, etc. This x11 is the reading from the first unit receiving the first treatment. Here the treatment is the factor under consideration, or here in the example it is fertilizer or the influence of the teacher. So if there are n1 observations receiving the first treatment, then x11, x12, etc., x1, n1 are the observations from the units receiving the first treatment. Likewise, x21, x22, etc., x2n2 are the observations receiving the second treatment. So in the first treatment is applied to n1 units, second treatment is applied to n2 treatments and n2 units, etc. Now, our aim is to discuss whether the fertilizer or that fertilizer is effect of fertilizer are equal in all these uh, rubber plants. For that we make use of analysis of variance. So we have the different types of causes influencing the yield of lactose. Here we say that even though all the factors influencing the yield of lactose are kept same, there are some causes which cannot be identified or which cannot be tracked, and such causes are known as chance causes. Next, we come to the main principle used in the formulation of analysis of variance. We have found that analysis of variance deals with a test for equality of means of several populations. So first, if you take only one factor as a topic of our discussion, it becomes a one-way classification or ANOVA for one-way classified data. So we have to discuss here one-way classification and also the two-way classification. In one-way classification, we have suppose n observations, that is in capital N observations, and this n is sum of 1 to k ni, where n1, n2, etc., nk are the number of units receiving first, second, third, etc., kth treatment. So the xij, the first suffix represents the order of the treatment, and the second suffix represents the order of the unit of our investigation. So if you list the observations in a table, it will be like this. If fertilizer 1 is applied to N1 rubber plants, and the readings are X11, X12, etc., X1N1, and total is T1. X21, X22, X2N2 are the observations which are subjected to fertilizer 2, and this X21, X22 represent the observations from these units receiving fertilizer 2, and its total is T2. It goes like that. Now, we assume that mu1, mu2, etc., mu-k are the averages of the populations subjected, receiving the first, second, etc., the kth treatment. So the null hypothesis in a one-way classified data will be H0, mu1 equals, mu2 equals, etc., mu-k. So the aim is to test whether all these k population means are equal or not. Therefore, we set the null hypothesis as H0, mu1 equals, mu2 equals to k, against the alternative hypothesis that the average effect of the treatments are significantly different. Now, for that, we propose a model for this one-way analysis of variance, and it is given by xij equals alpha plus mu I plus eij. We have found that this variation is the totality of assignable cause and chance cause. So here, this is sum of three factors. One is alpha. Alpha is supposed to be the common effect of all factors which are kept same. In the above example, we assume that the type of the seed or sapling or the other mean rainfall, sunlight, or the landscape, or many factors listed or unlisted. All those factors same, and their common effect is taken as alpha. As in the present case, we assume that the only factor influencing the yield of latex is fertilizer, and for the ith fertilizer, its influence is represented by mu I. That is the average of this average effect of ith fertilizer is mu I. So even though this fertilizer same for all plants receiving the ith treatment, so the total effect will be alpha plus, or total observation its value will be alpha plus mu I, but that is not same for all the units receiving ith treatment. So there is another factor called error factor, and that is EIJ. So the or totality of all these factors is considered to be the reading from the jth unit receiving ith treatment. So Xij is equal to alpha plus mu I plus Eij. So I repeat here, alpha is the effect of a common effect, or the total effect of all the factors which are listable or unlistable, and mu I is the average influence of the factor of our study, and Eij is the error factor. And the totality of all these three factors is supposed to be the value of these observations. Now we have different steps for this analysis of variance. Before that, we can come to the principle, some assumptions in the formulation of ANOVA. The first assumption is all the observations Xij are independent. Means never the observation from the unit receiving ith treatment and also the jth unit is not an indicative of this observation from any other unit receiving the same or any different treatment. So Xij's are independent to one another. Now next is this model Xij alpha plus mu I plus Eij for a one-way classified data, and the other important assumption is EIJs are normally distributed. EIJ means the error factor. It is said to be it is assumed to be normally distributed, that is normal distribution with mean 0 and standard deviation sigma. And the fourth assumption is the population from which the sample has been taken is normal. It's a very important assumption to apply this ANOVA. That means the all observations, we have only a set of observations, this is only a sample. So the sample observations are drawn from a population which is normally distributed. So now we are the main thread of this formulating this analysis of variance. We are not coming to the step-by-step derivation of various terms in various principles in analysis of variance. Only here we are considering the main principle or main theme of main theme in the formulation of ANOVA. Earlier we studied that in sampling distribution, mean of a sample, no, xi, not in sampling distribution, in normal distribution, xi minus mu by sigma follows n01. That is, if xi follows n mu sigma square, z is equal to xi minus mu by sigma follows n01, which is a standardization device. And the square of any standard normal has chi-square distribution with 1 degree of freedom. So here xi follows n mu sigma square, and chi-square equals sigma is equal to 1 to n xi minus mu by sigma square follows chi-square distribution with n degree of freedom. And this is a topic we had discussed in the sampling distribution. That is, I shall just refresh the topic of this sampling distribution, and that is the equation we are applying from the sampling distribution. So this is the point. Zi equals xi minus mu by sigma follows n01. That is, x1, x2, etc. xn are distributed n mu sigma. Then zi follows n01. Zi square follows chi square with 1 degree of freedom. Now z square is sum of the z1 square, z2 square, etc. zn square. So z square follows chi square distribution with n degrees of freedom. Now thereafter, we again come to another statistic which deals with the ratio of two independent chi-square random variables. That is in F distribution, we have this property: if chi-square 1 and chi-square 2 are two independent random variables following chi-square distribution, then f equals chi-square 1 by n1 divided by chi-square 2 by n2 follows f distribution with n1 and n2 degrees of freedom. So this is the statistic or the principle of standard analysis of variance. That is, f distribution is the statistic following the statistic used in analysis of variance follows f distribution. So in a question to answer the statistic for the statistic distribution in used in f in ANOVA is f distribution. So next is, it's known that it has ratio of two chi-square hybrids f distribution. Now we have a step-by-step procedure for doing the ANOVA for or the H0, mu1 equals, mu2 equals, etc. mu k. So the first step is finding the correction factor. As I told you, we are not coming to the various sum of squares, the observations or etc. because we have only a step-by-step procedure here. All these things are derived using that principle of uh, sum of squares of sum of squares of standard normal follows chi-square distribution, and also ratio of two chi-square random variables follow f distribution. So here the first step is setting a null hypothesis, and that is like all the population means are equal. So at 0 mu1 equals mu2 equals etc mu k. Secondly, we will do we'll compute the correction factor. The correction factor is 1 by n, sigma is equal to 1 to k, sigma j is equal to 1 to ni xij, which means that all this sum of all the observations that is taken first and its square, which that is, if you have the observations like this, x11 plus x12 plus etc x1n1 plus x21 plus x22 plus x2n2 etc, it comes up to the last row xk1 plus xk2 plus etc xknk. That is, sum of all the observations is taken first, that is by j equals 1 to n1. Now j is equal to 1 to n2, then j is equal to 1 to nk, and that is given in this sum of I is equal to 1 to k, sum of j is equal to 1 to ni xij, and that total sum square is considered here, and it is divided by n. N is the number of units in our study, and that is known as correction factor. Next is finding TSS, that is total sum of squares. In total sum of squares, we are finding sum of squares of the observations. That means here we will find out squares of observations. So first is x11 square, x12 square, etc. x1n1 square. Next row x21 square, x22 square, etc. x2n2 square, etc. Then after finding squares of these observations, next we find sum of these squares, and that is represented using this TSS, or sigma is equal to 1 to k, sigma j is equal to 1 to ni xij square minus c. So the subtraction of c stands for the subtraction of the correction factor. And this TSS has degrees of freedom n minus 1, because in this TSS there are n summands x11, x12, etc., x1n1, and next x21, x22, etc., x2n2, and it goes up to xknk. So there are n observations in this summands, and that n minus 1 is the degrees of freedom for this total sum of squares. Next is sum of squares due to treatments. So here we have to consider first of all the sum of rows of these observations, that is known as row sum, that is denoted by t1, t2, etc. tk, x11 plus x12 plus etc. x1n1, it is t1. That is, we are finding the sum of sum of the treatments. Now, yeah, that is, thereafter we have to find the squares of this sum, that is xi dot square. Xi dot means sigma j is equal to 1 to ni xij. There is a dot after I in the suffix. Xi dot is sigma j is equal to 1 to ni xij, or in the table it is equivalent to t1. Next we are finding squares of this xi dot. So xi dot square by ni. So if I is 1, x1 dot square by n1. Now I is 2, x2 dot square by n2, etc. And sum of these xi dot square by ni minus c is the value of sum of squares due to treatments. Next is the part of finding sum of squares due to errors. It is obtained by subtracting the sum of squares due to treatments from the total sum of squares, and it has n minus k degrees of freedom. Here this sum of squares due to treatments has k minus 1 degrees of freedom, because in this summation there are k summands 1, 2, 3 etc. K minus 1, that is the degrees of freedom of the sum of squares due to treatments. Therefore, this total sum of squares is given by this equation: sigma is equal to 1 to k, sigma j is equal to 1 to ni xij square minus z with n minus 1 degrees of freedom. Next is SST, that is sum of squares due to treatments. It is given by sigma is equal to 1 to k xi dot square by ni minus z, which has k minus 1 degrees of freedom. And next is SSC, which is obtained from the above two sum of squares, that is TSS and SST, that is TSS minus SST, and its degrees of freedom also this n minus 1 minus k minus 1. Here TSS minus SST. Therefore, degrees of freedom of n minus 1 minus degrees of freedom of SST, that is n minus k. Next, we are finding mean sum of squares. Mean sum of squares is simply the ratio of sum of squares obtained and the degrees of freedom. That is, VT is the mean sum of squares for treatments, and it is SST by the degrees of freedom of SST, k minus 1. Likewise, mean sum of squares due to errors is VE, that is sum of squares due to errors divided by its degrees of freedom, that is n minus k. That's about the mean sum of squares. Next, we are presenting all these things in a table called Anova table. That is Anova table for a one-way classified data. The first column represents the various sources of variation, that is treatment, error and total. And next is their notations: SST, SSE and TSS. Next column represents the degrees of freedom. So when we write the degrees of freedom, first we write sum of squares due to treatments, that is k minus 1, that is number of treatments minus 1. Next we have to write this n minus 1, because the total sum of squares and SST you can obtain from the values given. Sum of squares is to be obtained from the values based upon TSS and SST. Therefore, the order of entering values in the table: first SST, then TSS, that is k minus 1 here, then n minus k, n minus 1. And this n minus k is to be obtained from this capital N minus 1 minus k minus 1 and n minus k. And finally, you can check that k minus 1 plus n minus k will be equal to n minus 1. The same manner, first we write the sum of squares due to treatments here, SST here, the value compute from the set of observations. Next we write the TSS, that is sum of squares due to total sum of squares in this cell, and making use of these two entries, that is the total sum of squares and SST, we enter here the sum of squares due to errors, that is SSC, which is given by TSS minus SST. Also, you can check it by adding these two to see the value of total sum of squares. So that completes all sum of squares from the given set of observation. Next is the computation of mean sum of squares and also the F ratio. The mean sum of squares, as we discussed here, it is the ratio of the sum of squares to its degrees of freedom. So mean sum of squares due to treatments will be Vt is equal to SST by k minus 1, and Ve will be, that is sum of squares to mean sum of squares due to errors will be, that is Ve, that is SSE by n minus k. So next is the F ratio. We take Vt in the numerator and Ve in the denominator. So it is Vt by Ve, and this is like this and as in the principle of this ANOVA, we found that this is a chi-square random variable following k minus 1 degrees of freedom. This is another chi-square random variable, this is another chi-square random variable with n minus k degrees of freedom. So we are putting these two random variables following chi-square distribution in this F, that is F ratio is consisting of ratio of two random variables following chi-square distribution with k minus 1 degrees of freedom and n minus k degrees of freedom. The statistic, now the variable in the numerator has k minus 1 degrees of freedom and the denominator has n minus k degrees of freedom. So therefore the result here we found chi-square 1 by n1 divided by chi-square 2 by n2 follows F distribution with n1 and 2 degrees of freedom. Here we have this F, that is ratio of two Vt and Ve, has F distribution with k minus 1 and n minus k degrees of freedom. So from tables of F distribution, for example 5% level of significance, obtain the coincidence of the n1 k minus 1 degrees of freedom and n2 n minus k degrees of freedom, and we reject the hypothesis if f is greater than f alpha. The f is the value we compute using this Vt and Ve. F alpha is the value we obtain from tables of f distribution. So if f is greater than f alpha, uh, reject the hypothesis, and if f is less than f alpha, accept the hypothesis. If we accept the hypothesis, it means that all the treatments are equally effective, they are not significantly different, or in the example, or fertilizers are equally good in the yield of lactase. And if we reject the hypothesis, we say that the treatments are not equal in performing the level. That's the case of a one-way classified data. Next is Anova for two-way classified data. It's a slight extension of this one-way classified data into two-way classified data. Here, the difference is we consider two factors, separate factors, which influence the observation, the variation in the observations. So one is treated as the treatment and other is considered as the variety. So factor A is the treatment and factor B is the variety. So that will be a 2 by 2, I mean that will be an m by n table. Means here x11 is the observation receiving factor A or treatment 1, and this factor B or variety 1. So the suffix 1 goes to treatment, second suffix 1 goes to the factor, or xij is the observation from the unit receiving ith level of factor A or treatment and jth level of factor B or variety. So in the above example, if you consider two factors like the fertilizer and also the type of the sapling, then it's a two-way classified data. So that is a model for this analysis of variance, and before that we have the two null hypotheses, one for alpha 1 equals alpha 2 equals etc alpha m, and second for factor B, that is the variety beta 1 equals beta 2 etc beta n. So our assumption is all these factors, all the levels of the factors average are equal, and in the second part of the hypothesis all the levels of the factor B, that is variety, are equal. So we have the model xij is equal to mu plus alpha I plus beta j plus eij is a simple extension of the model we considered for a one-way classified data. So here mu is again the total effect of all the factors which are listed or unlisted, and alpha is the influence of the factor in treatment, and beta j is the influence of the second factor, that is variety, and eij, even though these are all same, we find some variations in observation, and that is assumed to be the effect of the error factor, so eij. Next we have the different levels here, which are all the steps are very identical to that of one-way classified data. H0 and H0 for the first factor, that is alpha 1 alpha 2 etc alpha m, and H0 for the second factor beta 1 beta 2 etc beta n. Now next is finding the correction factor, which is same as the case of one-way classified data. We find the sum of the entire observations and finding square of this sum of observations divided by n. N is here m into n because it is a m by n table. So that is number of rows into number of columns will be the value of capital N. Next we are finding the total sum of squares, that is the sigma I is equal to 1 to m, sigma j is equal to 1 to ni, xij square minus z. That is the total sum of squares. That is squares are found first, then finding the sum of the squares minus z, that is the correction factor computed earlier. And it has n minus 1 degrees of freedom. You can see that in this summand there are mn values, and mn is equal to capital N. So n minus 1 is the degrees of freedom of TSS. Next, we have the SSA, that is sum of squares due to factor A or treatments or rows. So here we find first the row sum, that is xi dot square. Now xi dot is sigma j is equal to 1 to n xij. That is in the table we are finding this total of the rows, that is x1 dot, x2 dot, etc., x3 dot or xi dot, that is denoted by sigma j is equal to 1 to ni, it's here j is equal to 1 to n xij, it is xi dot, and it has m minus 1 degrees of freedom because here m treatments in this m treatments here, so it is m minus 1 degrees of freedom. Next step, we are finding sum of squares due to the factor b, that is 1 by m, sigma is j is equal to 1 to n x dot j minus c, and x, this is not again xi dot, is a correction. I shall do the correction using the pencil. So this is to be considered as x dot j, x dot j, x dot is sigma, and this is also to be corrected. This side is sigma j is equal to 1 to n I xi is to be changed as summation, yeah, I is equal to 1 to m, 1 to m xij. So the first case is xi dot, that is j is equal to 1 to n xij. Second is x dot j, that is j I is equal to 1 to m xij. In the table we can see that it is the column sum x11 x21, therefore the index is, I mean the first index is getting changed and second index will be same for all the entries in the first column. That's why it is x dot j is equal to sigma is equal to 1 to m xij. So x dot 1 will be sigma is equal to 1 to m xi1 and so on. So after getting all these sum of squares, next we can find the sum of squares due to errors, that is SSE. SSE is obtained by subtracting SSA and SSB from TSS, and it has degrees of freedom m minus 1 into n minus 1. So our next step is finding the mean sum of squares. They are obtained by dividing the sum of squares with respective degrees of freedom. So for the first factor or treatment, it will be SSA by n minus 1. For the second factor, it will be SSB by n minus 1. And for the error factor, it will be SSE by its degrees of freedom m minus 1 into n minus 1. Next, we are entering all these values in the Anova table for a two-way classified data. As before, the titles here, the source of variation and their abbreviations, and here the degrees of freedom. Here also first we will enter m minus 1, then n minus 1, then capital N minus 1. Now from capital N minus 1, we have to subtract n minus 1 and m minus 1 to write the degrees of freedom corresponding to the error factor. That is, it's not the order like m minus 1, n minus 1, m minus 1 and n minus 1 and capital N minus 1. We are getting the degrees of freedom of error by subtracting the degrees of freedom of SSA and SSB from the degrees of freedom of TSS. Therefore, the degrees of freedom of SSC will be n minus 1 minus n minus 1 minus m minus 1, which is m minus 1 into n minus 1. Likewise, this is the same order for writing the various sum of squares. First write the sum of squares due to the first factor or treatment and the variety sum of squares, that is SSB, and sum of these two are subtracted from the total sum of squares to get the sum of squares due to errors, that is TSS minus SSA minus SSB. Next is the mean sum of squares, that is by dividing each sum of squares by their respective degrees of freedom. So here SSA by m minus 1, here SSB by n minus 1, and here SSC by m minus 1 into n minus 1. The next we have two F ratios. One is the first factor, that is treatment mean sum of squares by that is error sum of squares. Next is variety sum of squares, that is factor B, so mean sum of squares divided by error sum of squares. And the same principle of relation connecting chi-square distribution and F distribution is considered. So first is f greater than one, there are the two values of f here, one is f1 and second f2, and if f1 is great, fa is greater than f1, we reject the hypothesis, otherwise we will accept. Likewise, if fb is greater than f2, we will reject the hypothesis, otherwise we will accept that. So that's about the analysis of a two-way classified data. Examples also will be discussed.